Today we're going to look in more detail at some of the functions that we started talking about with the function families and learn how changing things around will change them. In particular, we're going to talk about power functions, things that involve x to some exponent. And we'll talk about the basic shapes of power functions and then how you can transform them by throwing different numbers into the mix. The most important thing about a power function is what kind of exponent it has, and in particular, whether that exponent is odd or even. We looked before at the graph of x squared and x cubed, and basically every even function is going to be a lot like x squared, every odd function is going to be a lot like x cubed. So if you have a problem like x squared, x to the fourth, x to the sixth, x to the 24th, anything like that, you're going to have something where a graph looks a lot like a parabola. We already did the graph of y equals x squared, and of course it was a very simple parabola. It went through the origin, it went up on both sides. That was the graph of x squared. Here you're looking at three other even power functions. I have x to the fourth, x to the sixth, and x to the 14th power. And if you look at those graphs, you'll notice they all have the same basic shape. X to the 14th looks a little weird when I graph it on the calculator, but it still is going to end up touching at the origin. It's because it honestly goes up so fast that the calculator can't show it as well. There are 3 points that are on every one of these functions. Those are the points 0, 0, 1, 1, and negative 1, 1. That's because if you take 1 to any power at all, the answer is 1. 0 to any power at all, you get 0. And if you take negative 1 to any even power, the negative cancels and you get 1. You always get a U-shaped graph that's reflected over the y-axis when you have an even power function. The domain will always be all real numbers, negative infinity to infinity, and the range will always end up being, it says here positive real numbers, technically it's non-negative real numbers. If you wrote it out, you'd have a bracket at 0 and go from there to infinity. Because of that U-shape, the graph falls on the left, it rises on the right, it's decreasing when x is less than 0 and increasing when x is greater than 0. What happens when you have a bigger exponent is that U-shape just goes up quicker. You have steeper sides and it looks narrower. It's still going to go on forever in both directions, but it goes up much, much faster when you start putting in bigger exponents. The other thing that happens is that when you put bigger exponents in, it becomes flatter between negative 1 and 1. That's because if you take a power of a fraction, you get a smaller fraction. If you think about it, if you take like 1/2 squared, you get a fourth. If you take 1/2 to the fourth power, you're going to get 1/16, which is even smaller. And so the bigger the exponent, the smaller the fractions you get when you plug in numbers between negative 1 and 1. So you can ponder what it would look like if you did a really big exponent like x to the 100th power. And it really does look like it just goes straight up. And because it's so close to the x-axis at the bottom, you really can't see anything that's going on down at the bottom. It does almost look like a cross-section of a tire where you're really just sort of looking at a flat tire head on. So very, very flat in the middle, and then rising almost straight up. Technically, those lines are curved very slightly, but not much. That's because if you tried to take 2 to the 100th power, you've got such an enormous number, it just is way off the screen. There is a word for that sense of flatness that you see in the middle. We call that contact with the x-axis. And it does turn out that the bigger the exponent is, the more contact you have. Big exponent, big contact, small exponent, small contact. And of course, bigger exponents will make the graph rise faster. In your book, they'll sometimes call that exponent the degree. So if you have a higher degree, you're going to have more contact. If you have a higher degree, the function is going to rise faster in its graph. I also want to talk about what happens with odd exponents because basically it's the same thing, but it's a variation on the x cubed graph. We've looked at the graphs of y equals x and also the graphs of y equals x to the third, and you probably know that both of those go through the origin and they go from the third quadrant up to the first quadrant. Well, it turns out that every other odd power function is going to be very similar. I have the graphs of x to the fifth and x to the 17th here, and you can see they also start in the third quadrant and go up to the first quadrant, but the difference with them is how fast they do it. For odd power functions, you're always going to have the points 0, 0, 1, 1, and -1, -1 on the graph. That's because when you take negative numbers to an odd power, the answer is going to be negative. Both the domain and the range will end up being all real numbers because eventually you'd go all the way from the left to the right, and you can tell very easily that you go all the way from the bottom to the top. So negative infinity to infinity, that's the domain, and it's also the range. Odd power functions have graphs that are always rising, they're always increasing, but they slow down and kind of flatten out in the middle. You go up really fast, you slow down right around the origin, and then you go up fast again. Just like with the even ones, the bigger the exponent is, the faster it's going to rise. And also, the bigger the exponent is, the flatter it's going to be, the more contact you have near the x-axis. Here I tried to graph x to the 101st power, and you can still kind of see that same shape of starting in the third quadrant and going up to the first quadrant. This time it's so steep that it literally looks like two vertical lines. They would technically be very slightly curved, and it would flatten out and go at a more diagonal rate, but again, it still is very flat in the middle. And it does turn out that even the line y equals x or y equals x to the first is really just an odd power graph. It doesn't have that sort of curving at all, but it still starts at the third quadrant, goes into the first quadrant, and it goes through -1, -1, 0, 0, 1, 1, same basic shape. So here you can see variations on all of the odd and even power functions. Just like you've learned to do with things like trig functions last year, you can transform power functions. You can move them around, you can stretch them out, you can make them be different but still have the same basic shapes. One way you can transform functions is to put a number at the end. And if you add a number to the end of a power function, what it does is it pushes the graph up or down. We have what we call a vertical translation. In trig, we call that a vertical shift. You just take the whole graph and you push it up or down by the same amount. On the left, I have x to the fourth minus 5, and you notice the bottom of the graph is at -5, and it's that same U shape we had for an even power function. On the right, I have x cubed plus 2. It's that same basic x cubed graph, but this time it turns the corner in the middle at 2 instead of at the origin. So a number at the end, you go up or down by whatever that number is. If you happen to have a number in parentheses, what ends up happening is it moves it left to right, but importantly, it moves it the opposite way of what that number says. What you're looking at is x minus 4 to the 5th power. And you see the odd power function, but the x minus 4 ended up actually moving it so that it turns the corner at +4 on the x-axis. You've encountered that before too, when we were doing all of the conic sections that we did online last year, and when we worked with circles in that first chapter of the analysis book, you always did the opposite of anything that was in parentheses. So you might ponder what would happen if you did both of those things. Here it's asking, what would you have if you did x plus 2 to the 10th power minus 3? And obviously we've got the plus 2 that matters, we've got the minus 3 that matters, and it matters that the function is 10th power. Well, I know because it's an even power function that it's going to be U-shaped. It's going to be a lot like a parabola. And it's actually going to go up pretty steeply and be pretty flat at the bottom. And this time the bottom of that U will be at the point -2, the opposite of what's in parentheses, and -3 from what's at the end. Here you can see that graph, and all those things I just said are true. U-shape that's flat at the bottom and goes up fast, and again it moved to the left 2 and down 3. One other way that you can change around functions is by putting a coefficient, a number in front of the x. So like here, I started off with x to the 7th. In the middle, I have 0.001 x to the 7th. And at the right, I have 3x to the 7th. Well, what happens is the middle one, it's still an odd power function, but it's fatter. It goes up much more slowly. On the other hand, when I put 3x to the 7th, it's skinnier. It goes up way faster. So yeah, a whole number is going to make it go up faster. A decimal or fraction will make it go up more slowly. And if you do throw in a negative exponent, what it does is turn your graph upside down. Again, that's something that happened when we were in trig as well. Negatives just mean do the opposite. So like negative 0.25 x to the 6th, it's an upside down U-shaped graph that's a little bit fatter than what it normally would be. So that's the crash course in how functions and their graphs work. Hopefully that gets you caught up on the stuff that you've missed recently, and there's a worksheet that'll go with these that talks about different kinds of functions and how you can change them around.